Welcome to my YouTube channel. We are going to discuss today about the semiconductor devices. Basically, we will study about the PN junction diode and its working, forward biasing and reverse biasing. In the previous class, we have seen about the two types of semiconductor, that is intrinsic semiconductor and extrinsic semiconductor. And then we have seen about the P-type extrinsic semiconductor and N-type extrinsic semiconductor. So basically, before going into detail about the working of PN junction diode, first we are going to derive an important result, that is how we can prove this relationship. So first we will study about this simple derivation to prove NH into NE is equal to NI square. We are going to prove this result where NH is equal to number of holes, Ne is equal to number of electrons, and Ni is equal to number of intrinsic charge carrier. Intrinsic charge carrier. So in the previous video, what we have seen, in case of intrinsic semiconductor, basically number of holes and number of electrons are same. Both are equal in number. So let's derive this important result. So we know for intrinsic semiconductor, for pure semiconductor, this is the relationship. Semiconductor, number of electrons is equal to number of holes. Ne is equal to Nh, and that is basically equal to number of intrinsic charge carrier. This is the important result we have already seen when we have discussed about the intrinsic semiconductor or pure semiconductor. In pure semiconductor, what we have seen, when an electron is freely available, then simultaneously one positive charge is induced at that point. Basically, the number of electrons and number of holes. This is the process of generation of electron and holes pair in case of pure semiconductor. At the same time, one more process is going on. That is the recombination. Recombination means combination of holes and the electrons. The first process in case of intrinsic semiconductor is the generation of electron and hole pairs. At the same time, there is recombination also. So now we can see what is the rate of recombination. So rate of recombination, basically it is directly proportional to product of number of electrons and number of holes, Ne into Nh. And when we remove this proportionality, rate of recombination, when we remove this proportionality, there is a proportionality constant R and Ne into Nh, where R is here, R is a proportionality constant. A constant is there. So this is the result for intrinsic semiconductor. Now for the extrinsic semiconductor, we can write down the rate of combination. For extrinsic semiconductor, we can write down this result. For extrinsic semiconductor, the rate of recombination, basically it will be directly proportional to the number of electrons and number of holes, because electrons and holes are basically the charge carrier. Now when we will remove this proportionality constant, rate of recombination, then it will be equal to directly proportional to, when we will remove this proportionality constant, it will become R into Ne into NH. Here again R is a proportionality constant. But in case of intrinsic semiconductor, what we have seen, when we can write down this equation, R into Ne into NH, number of electrons is equal to Ni, and number of holes, it is also equal to Ni. So basically we can write down R into Ni square. Okay, this will be our equation number 1, and this will be our equation number 2. And from equation 1 and 2, what we can write down? From equation 1 and 2, we can write down basically R into Ni square, right hand side of the equation 1 and right hand side of the equation 2, it is equal to R into Ne into NH. R will be cancelled out from both sides, and then we will obtain this result. Ne into NH, it is basically equal to Ni square, number of intrinsic charge carriers. So the product of holes and the electrons in any semiconductor, whether it is extrinsic or intrinsic semiconductor, that is basically equal to the square of the intrinsic charge carrier concentration. So this is one of the important result just we have proved. Now we are going to a important topic now, that is PN junction diode. So before going into PN junction diode, you must know about the p-type semiconductor and n-type semiconductor that I have already explained in the previous video. So now our next topic is the PN junction diode or simply diode. PN junction diode, or simply we can say it diode also. So how a PN junction diode is formed? So we can write down, when p-type semiconductor, when p-type semiconductor is combined with n-type semiconductor, PN junction diode is formed. PN junction, or simply PN junction, we call it PN junction diode is obtained. Now let's see the constructional details, how the PN junction diode is made or manufactured. So basically it is combined where PN junction diode is formed when p-type semiconductor it is combined with n-type semiconductor. When p-type extrinsic semiconductor is combined with n-type semiconductor, PN junction diode is formed. Now this is the simple diagram we are going to discuss, how a PN junction diode is formed. Let me draw with the diagram. So this is your p-type semiconductor. Let me take the p-type semiconductor. This is your p-type semiconductor. Now this p-type semiconductor, it is combined with n-type semiconductor. You can see there, it is combined with, just wait for a minute, it is combined with n-type semiconductor. Okay, it is combined with n-type semiconductor. Okay, p-type, it is combined with n-type semiconductor. Okay, when p-type semiconductor is combined with n-type semiconductor, a PN junction diode is formed. This is the junction, you can see it there. This is the junction. Here one junction is formed. This junction is known as PN junction. This is your p-type semiconductor. This is your p-type semiconductor, and this is your n-type semiconductor, and this is your junction. Near the junction, one charge free region is there. That region is known as depletion region. I will explain it later on. Positive, negative, positive, negative, positive, negative. And this region, this is basically the junction. This region is known as depletion region. Depletion layer, it is called as. Now this p-type and n-type semiconductor, they are joined with the metallic plates. These are the plates. These are the two plates. Metallic plates are there, metallic contacts are there, and from here wire is soldered to take out the connection from p-type and n-type semiconductor. You can see it there. These are basically your metallic contacts. This is your metallic contact to the p-type semiconductor. It is also your metallic contact. And from these two metallic contacts, connections are taken out like this. You can see here. These are the connections taken out from the p-type semiconductor and n-type semiconductor. So this is the process of manufacturing of PN junction diode. How a PN junction diode is manufactured? When p-type semiconductor is combined with n-type semiconductor, then we get a PN junction. This point is known as junction. And in order to get out the connection from p-type and n-type, just two metallic contacts are there, and from these two metallic contacts, two wires are taken out. And this is the symbol of the PN junction diode. A PN junction diode, it is represented by this symbol. For p-type, we are using, so this is the symbol of PN junction diode. This is your p-type semiconductor. P-type semiconductor, it is represented by a triangle, and we have n-type semiconductor. N-type semiconductor, it is represented by a vertical line. This is your vertical line. You can see it there. It's not. Yeah, this is your n-type semiconductor. And two connections are taken out. One from p-type, another from n-type. These are the connections. One from p-type, another from n-type. Okay, so this is the symbol of the PN junction diode, or simply we call it as diode. This is your anode and this is your cathode. So basically diode is a two-terminal device, diode, and it always conducts in only in one direction. It cannot conduct in both directions. We will study it later on. So this is the symbol of PN junction diode. Symbol of a diode. Okay, so this is all about the PN junction diode. Now we know about the p-type semiconductor and n-type semiconductor. In case of p-type semiconductor, they are negative ions, means there are electrons which are majority charge carrier, and in case of n-type semiconductor, there are in p-type, holes are majority charge carrier, and in n-type semiconductor, electrons are majority charge carrier. It doesn't mean that there are no holes and electrons in either side of the electron, either side of this PN junction diode. Basically, we will study in detail now. In case of p-type semiconductor, in the p region, basically in p region of PN junction, there are negative ions. There are negative ions fixed in their position. Means negative ions are fixed in position. Fixed in their positions. Fixed in their positions. Surrounded by holes in case of P region of the PN junction diode, and holes are mobile charge carrier here in this case. Similarly in in N side or N region of PN junction diode, PN junction diode, there are holes. These are the positively charged ion. There are holes which are fixed in their position, which are fixed in their position in their crystal lattice, in crystal lattice, surrounded by mobile electrons, surrounded by negatively charged ions, surrounded by negatively charged ions or electrons, we can say. Now when p type and n type are brought in contact with each other, then what will happen? When p type semiconductor, or when p type and n type semiconductor to form the junction, when p type and n types semiconductor are brought in contact, are brought in contact are brought in contact to form to form PN junction, to form PN junction, the holes and electrons move due to thermal diffusion. The holes and electrons move due to thermal diffusion. Positive charge and negative charge, they will diffuse and thermal energy is produced, and due to this thermal diffusion, what will happen? The electrons and holes will start moving. The holes and electrons move due to thermal diffusion, due to thermal diffusion. At the term diffusion means when an electron collide with the positively charged particle, then diffusion take place, or vice versa. When a positively charged particles will collide with an electron, diffusion will take place. So due to the thermal diffusion, the electrons and holes will start moving near the junction, at the junction. And at the junction, now we will get the charge free region. The positively charged holes, the positively and negatively charged ions, negatively charged ions meet, they cancel out the effect of each other. They cancel out the effect of each other, thus forming thus forming a charge free region, a charge free region near the junction, near the junction, which is known as depletion layer, and this charge free region is known as depletion layer. And how this depletion layer is formed? Due to the thermal diffusion of the electrons and the holes to the either side of the junction, basically the holes and the electrons, the positively charged holes and the negatively charged electrons, they will meet near the junction, and they will cancel out the effect of each other, and near the junction one charge free region will be formed. That region is known as depletion region. Now Just we have seen p-type semiconductor and n-type semiconductor combined together to form the p-n junction diode. So p-type holes are majority charge carrier, and in n-type the electrons are majority charge carriers. So there is a potential difference. Okay, and this potential difference between the ends of semiconductor diode is known as potential barrier. So now we can define the potential difference. The potential difference, the potential difference, the potential difference across the ends of semiconductor diode is termed as barrier potential. It's termed as barrier potential. So this is all about the PN junction diode. So now we are moving forward to study about the forward biasing and reverse biasing. In order to make the diode conduct, we need to connect this conductor, or we need to connect this diode basically with the external source of energy to a battery. Now in the manner in which we are connecting this diode with the external source of energy or battery, the term is known as forward biasing and the reverse biasing. Okay, because diode is a two-terminal device. So in the manner in which we are connecting the battery to this diode leads to the forward biasing and reverse biasing. First, what is the biasing? Biasing is nothing but connecting a diode to the external source of energy or to external battery is nothing but the biasing. So now we are going to study about the forward biasing and reverse biasing of the PN junction diode. So now we will see the biasing. What is the meaning of biasing here? Just first we will see what do you mean by biasing. So biasing first we will see. So biasing is nothing but connecting. There are two types of biasing we will see about the PN junction diode. One is known as forward biasing and other is known as reverse biasing. These are the two types of biasing. Now what is the meaning of the biasing here? Biasing is nothing but connecting the terminals. Two terminals are there in diode. Terminals of a diode, PN junction diode, to the terminals of a battery. In battery also there are two terminals. Terminals of a battery, that is known as biasing. And basically there are two types of biasing. One is known as forward biasing and other is known as reverse biasing. Now let's see what is forward biasing. Okay, so simple diagram I will represent, then we will see in the detail. So this is your diode. This is basically our diode. Now what we are doing, this is P type and this is N type. And here also in case of reverse biasing, P type and N type, and these are the terminal. Two terminals are there. It is a two-terminal device. It has also got the two terminals, anode and cathode. Okay, now what we are doing? Now we are connecting it with the external source of energy with the wire. Now we are connecting P-type semiconductor with the positive terminal of the battery, and N-type semiconductor. Now it is connected with the negative terminal of the battery. Then this process is known as forward biasing. Suppose the EMF of this battery must be greater than potential barrier. Always remember this value must be greater than the potential barrier. I will explain in detail about this forward biasing. Now In case of reverse biasing, the p-type semiconductor, now it is connected with negative terminal of the battery, and this n-type semiconductor, it is connected with the positive terminal of the battery, negative, positive. Then this process is known as reverse biasing. So these are the two types of biasing. Now we will study about the forward biasing and reverse biasing of the PN junction diode in detail. Basically, this is your p-type semiconductor, this is your n-type semiconductor, this is p-type and n-type. In case of forward biasing, p-type is connected with the positive terminal of the battery, and n-type it is connected with the negative terminal of the battery. In case of reverse biasing, the process is just reverse. The p-type semiconductor now connected with the negative terminal of the battery, and n-type semiconductor now it is connected with the positive terminal of the battery. Then the process is known as reverse biasing. Now we will study about the forward biasing and reverse biasing in detail. So first we will see the working of PN junction diode in forward biasing. So first we are going to study about the forward biasing of the PN junction diode. So let's see about the forward biasing of PN junction diode. Forward biasing of PN junction diode. Let me draw the diagram first. In case of forward biasing, so this is the forward biasing. Let me choose the p-type semiconductor first. This is our p-type semiconductor, and we have n-type semiconductor also. When they are combined together, we get the PN junction diode. This is our n-type semiconductor. You can see it there, and this is the junction basically. Now p-type semiconductor, it is combined with n-type semiconductor. Then we will get the PN junction diode. In case of p-type, this is our p-type semiconductor, and this is our n-type semiconductor. In case of p-type semiconductor, basically the main current carrier or main charge carriers are holes. Positively charged holes are there. Positive, 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 positive. You can see it there. These are the positive ions, holes. And in case of n-type semiconductor, electrons are there. Minus, minus, minus. You can see it there. These are the negatively charged ions or electrons basically. You can see it there. And this is the junction area. Basically, this is your PN junction. This is your PN junction. And here also we can draw the electrons and holes crossing the junction. Minus, plus, minus, plus. And here this region is charge free region, because negative charge ions will cancel the effect of positive charge ions, and here we will get the depletion layer. The depletion layer width is less in this case. This layer is known as depletion layer. Depletion layer. Now what we are doing? Now we are connecting this p-type semiconductor with the positive terminal of the battery. These are the metallic contacts. Metallic contacts I have not drawn here. This is your metallic contacts from p-type semiconductor, and here it is also metallic contacts at the n-type semiconductor. Now wires are taken out. These are the wires. Now forward biasing, in case of forward biasing, p-type semiconductor, it is connected with the positive terminal of the battery, and n-type semiconductor, it is connected with the negative terminal of the battery. Okay, p-type semiconductor, it is connected with the positive terminal of the battery, and n-type semiconductor, it is connected with the negative terminal of the battery. Then this process is known as forward biasing. So this is the case when a PN junction is forward biased. So what happens when a PN junction is forward biased? First we will see what is a forward biasing. So when a battery of EMF greater than barrier potential is connected in such a way that the positive terminal of the battery is connected to p-type semiconductor, and negative terminal of the battery is connected with n-type semiconductor, then PN junction diode is said to be forward biased. So when the PN junction is forward biased, when p-type semiconductor is connected with the positive terminal of the battery and n-type semiconductor is connected with the negative terminal of the battery, provided the EMF of the battery that we are connecting with the diode must be greater than the barrier potential. So this is all about the forward biasing. This is a simple process of forward biasing. Now what happens when it is forward bias? So when the PN junction is forward bias, this positive terminal of the battery, you can see it there. Let me explain it. Since this is forward bias, this p-type semiconductor is connected with the positive terminal of the battery, so these holes will be repelled to cross this junction. Okay, they will move. This is the movement, this is the direction of movement of the holes. And these electrons, because n-type semiconductor, it is connected with the negative terminal, so negative there will be repulsion, so these electrons will also compelled to cross the junction and to enter into the p-type. When they will cross the junction, near the junction, some of the electrons will collide with the positively charged ions and there will be diffusion of the electrons with the holes. And once they will cross the junction, the path of the charged particle, it will be completed and this diode will start conducting. So this is the process of working of the diode in case of forward biasing. So let's see in the detail the working of PN junction diode in case of forward biasing. Okay, so generally what happens, the holes from P side, now when it is forward bias, the holes from P region are are compelled to N region, while electrons from while electrons from n region or n site are compelled to p region. Near the junction, what will happen when they will compelled? They will cross the junction, and near the junction, some of the electrons will diffuse with holes and thus forming a layer depletion layer, which is thin in this case, which is thin. Now since the path of the holes and the electrons are completed, holes and electrons now flow in a complete path and diode will conduct. So what will happen? Now holes and electrons complete a path and diode thus conducts. In this case, diode thus conducts, provided the applied voltage is greater than the barrier potential. So this is the process of working of PN junction diode in case of forward biasing. Now we will see about the relationship between the current and voltage. We will draw the characteristics of current and voltage. We will study the relationship of applied voltage and its characteristics. Now we are going to draw the circuit diagram first. So let's draw the circuit diagram during forward biasing. Circuit diagram during forward biasing of a diode. Forward biasing. So first we will take the diode here. This is our diode. This is our diode. This is our diode. Two terminals are there. Okay, this is our PN junction. Now we are connecting it. Okay, now P type, it is connected with the positive terminal of the battery, and N type, it is connected with the negative terminal of the battery. One ammeter we will connect here, milliammeter. One battery is here, and one voltmeter is connected to measure the potential difference. You can see it there. Okay, now we will connect everything now. Here one voltmeter is connected to measure the potential difference, and here one ammeter is connected, milliammeter, to measure the current. Okay, and this is our battery, biasing battery, positive, negative, positive, negative. It is a variable battery. So this is the circuit diagram of the PN junction diode. This is our p-type semiconductor and this is our n-type semiconductor. Now it is forward bias. Now we will draw the characteristics during the forward biasing and reverse biasing. Let me draw the axis. This is the axis, x-axis, and this is our y-axis. You can see it there, y-axis. So now we will take the current along y-axis, IV characteristics basically. This is the current along y-axis in milliampere and potential difference along x-axis in volt. Now we can take the intervals. Now we are taking the intervals of 0.2, 0, 0.2, 0.4 volt, 0.6, 0.8, then 1 volt, and similarly current we can take 20, 40, 60 and 80. So initially when it is applied with the external source of energy, the diode will not start suddenly, it will start conducting. There is a process also. Here what will happen, when we apply 0 voltage there will be no any current. Now we are increasing the potential difference, 0.2 voltage, still we are not getting the current. 0.4 volt, still we are not getting the current. 0.6 volt, still we are not getting the current. Now 0.7 volt, now the diode suddenly starts conducting like this. And if you will increase just a little bit voltage, the current will increase heavily. So this is the characteristics, IV characteristics of a PN junction diode. So this is your IV characteristics of a PN junction diode. And this voltage, the voltage at which this diode will start conducting, that is known as cut in voltage. This voltage basically it is known as cut in voltage, or sometimes it is also known as threshold voltage. Threshold voltage. The value of this cut in voltage is basically approximately 0.7 volt. This cut in voltage is approximately 0.7 volt for silicon, and this value is approximately 0.2 volt for germanium. So this is all about the working of a PN junction diode in case of forward biasing. Now we will move to the reverse biasing of the PN junction diode. Now we will see about the reverse biasing of the PN junction diode. So the next topic is reverse biasing of the PN junction diode. Next is reverse biasing of PN junction diode. First we will see the reverse biasing, the process of reverse biasing of the PN junction diode. So first we will choose two semiconductors here, p-type semiconductor and n-type semiconductor. This is our p-type semiconductor, and we have other n-type semiconductor also. This is our n-type semiconductor. This is our n-type semiconductor. These are the metallic contacts. You can see it there. Here we have metallic contacts. You can draw the metallic contacts and two wires are taken out. Metallic contacts are there. Okay, and this is your p-type. In case of p-type, the holes are majority charge carrier. This is our p-type semiconductor, an n-type semiconductor. Now they are reverse biased. So these are the holes. Holes are majority charge carrier in case of p-type, and this is your n-type. Electrons are majority charge carrier in case of n-type semiconductor. You can see it there. This is our p-type semiconductor, and this is our n-type semiconductor. Now we are connecting with the external source. We are connecting with the external battery. Now this p-type, it is connected with the negative terminal of the battery, and this n-type, now it is connected with the positive terminal of the battery. When it is connected like this, then the process is known as reverse biasing. Now p is connected with the negative terminal, and this n-type, it is connected with the positive terminal, and this is our junction. So what will happen when it is reverse biased? Now this electrons and holes from p side and n side, they will be attracted by the negative terminal and the positive terminal of the battery. You can see it there. These holes, these electrons will start moving away from the junction because they will be attracted by the negative terminal of the battery. These electrons, these holes will move away from the junction, and similarly the electrons from n side, they will start moving away from the junction. Like this, you can see when they will start moving away from the junction, near the junction there will be charge free region. No charge will be available near the junction. Here you can see here, due to the thermal diffusion also, if some of the electrons and holes will cross the junction, they will cancel the effect of each other. So here you will get a charge free region because number of electrons and holes both will cancel out each other. Here you can see it there, it is a charge free region. Holes in the n side and electrons to the p side, they are cancelling the effect of each other, and during the reverse biasing, basically this region will free from any charge, and here you will get one region that is known as depletion region, and here width is more. This is your depletion layer. Depletion layer. And if you will keep on increasing the reverse voltage, one stage will come when there will be breakdown and the diode will start conducting. So this is the process of reverse biasing. What is reverse biasing? When p region of the diode is connected to the negative terminal of the battery and n region of the diode is connected to positive terminal of the battery, pn junction diode is said to be reverse bias, just the reverse of previous problem. Now what will happen when it is reverse bias? So basically what will happen, the holes from p region, the holes from p region are pulled away from junction, as well as electrons from n region are pulled away from junction. We can say that. And thus depletion layer is formed near the junction because the junction will free from any charge. And thus in this way, and thus depletion layer will be formed near the junction, near the junction, which is thick, which is thick. Okay, so this is all about the depletion layer near the junction. In this case, the diode will not conduct. Why the diode will not conduct? Because they are moving away from the junction and there is no any complete path for these positively charged and negatively charged ions. Current requires a closed path. In this case, you can easily say that in this case, diode does not conduct. Why diode does not conduct? Because it is not getting the closed path. Okay. But if applied voltage, but if applied voltage is increased, but if applied voltage is increased, breakdown will occur. The holes and the electrons that they are fixed in their lattice, they will get the sufficient energy due to the thermal heating of the diode, and breakdown will occur. Increased breakdown will occur and the minority charge carrier will cross the junction and diode will start conducting. The voltage at which the diode will start conducting, that is known as reverse breakdown voltage. So this is all about the working of the PN junction diode during the reverse biasing. During the reverse biasing, the PN junction diode will not conduct provided the reverse voltage is less than, or the reverse applied voltage is less than the breakdown voltage of the diodes. So now first we will see the circuit diagram during the reverse biasing. So this is the circuit diagram during the reverse biasing. Let me draw the circuit diagram. This is our p-type semiconductor, and here we have n-type semiconductor. This is your diode, basically PN junction diode. Now we are connecting this PN junction diode. Now two terminal device, it is a two terminal device. This is your first terminal, you can see it there. So second terminal, cathode and anode is there. This is our cathode and this is our anode. Now what we are doing, now we are connecting with the external source like battery. Suppose here is one battery, variable battery is there. This is your negative terminal, positive, negative, positive. In the reverse sense, now we are connecting. Now what happens, now we are connecting it. Now n-type semiconductor, it is connected with the positive terminal like this, you can see it there. And here is one ammeter is also there to measure the reverse current. You can see it there. Now it is connected. Now 1 voltmeter is also connected to measure the potential difference. Here is one voltmeter is there to measure the potential difference. So this is the circuit diagram during the reverse biasing. Here one voltmeter is connected and here ammeter is connected in series. So here one micro ammeter is connected and this is your positive terminal, this is your negative terminal. So this is the circuit diagram during the reverse biasing. We can connect a switch also, and this is your variable battery. This is your variable battery. Now we will draw the reverse breakdown characteristics or the characteristics of this diode during the reverse biasing. So this is your fourth quadrant. It will be drawn in the fourth quadrant because both the voltage and the current we are applying in the negative direction, in the negative sense. So IV characteristics we are going to draw. This is the current and this is your, sorry, this is your current here. This is your current I and this is your voltage. Current in negative direction, it will be in microampere, and voltage reverse breakdown, reverse in reverse direction we are applying. voltage now we can take 20, 40, 60, 80, like this we can take the voltage. Now what happens for the small value of voltage, reverse voltage, the diode will not conduct. Okay, but if you will keep on increasing the reverse voltage, one stage will come when the diode will suddenly start conducting. Okay, this is known as reverse breakdown. Reverse breakdown. Suddenly the current will increase heavily, and this breakdown voltage, this voltage, it is known as reverse breakdown voltage. This new point is known as reverse breakdown voltage. So this is all about the reverse biasing of the PN junction diode and its characteristics, IV characteristics during the reverse biasing. So today in this video we have discussed about the forward biasing and reverse biasing of the PN junction diode, as well as their working during the forward biasing and the reverse biasing. So in the summary, what we can say about the forward biasing and reverse biasing, we can say that in forward biasing the diode will conduct, and in case of reverse biasing the diode will not conduct if the applied voltage is less than the reverse breakdown voltage. So this is all about the forward biasing and reverse biasing. So in the next video we will study about the application of the PN junction diode, what is the application of the diode, and that's all from the today's class. Thank you everyone for watching.